Hi, okay, so thank you very much for joining today, or this afternoon, this morning. My name is Neil Fitzgibbon. I'm the Optics Business Development Manager, and through this webinar I'd like to take you through how you can check for astigmatism with the PGI Optics. Okay, so I'm just going to hang on for a moment or two more. I think we've got a few more people joining, so just bear with me a minute. Okay, well, I'll get started then. So just to run through that again, my name is Neil Fitzgibbon. I'm the Optics Business Development Manager at Taylor Hobson. And through this webinar, I'd like to take you through an example of how you can check for astigmatism with the PGI Optics. Okay, bear with me one moment. I'll actually get the... There you go. Sorry about that delay. I was just getting the presentation moving. Okay, so first of all, what I'll do is I'd like to take you through a brief overview of the Taylor Hobson optics instruments and the range that we have. Then I'll go through the main body of the webinar, and that will be just demonstrating how you can manually check for astigmatism with the PGI Optics, which is a two-dimensional or 2D profilometer. And then to finish off with, I'll just give you an example of how you can use Zernike Analysis on the surface or on the measurements that you've taken, although we take the measurements in 2D. Okay, so at Taylor Hobson, we're very lucky because we have what I would like to think of as the widest range of instruments, optics metrology. We start with the PGI Optics, which is based on the form Talyprofile, which has been around for a good number of years now, and is really the fundamental go-to instrument for all optics shops. It's versatile, it's quick, it's easy to use, and you can measure pretty much any form as long as you can track it with the stylus. Moving up from that, we go to the PGI Matrix. Now the PGI Matrix builds on the PGI Optics, and that gives you the ability with automation, with the addition of a Y and a rotary stage. It gives us the ability to measure volume parts, i.e. we can do wafer level lens arrays, we can pick out individual lenses or measure every lens on an array. We can do micro lens arrays, or we can indeed do batch arrays or batches of parts, okay? So individual part arrays. Then we go on to the PGI Freeform, which is a very exciting instrument at the moment, and that builds again on the matrix and the optics, but we go one step further, and with this and with the addition of a more advanced linear motor air bearing Y stage, we have the automated capability to actually do a raster scan over a component and generate a 3D surface for that component. The good thing with the PGI Freeform is as long as we can scan it, then we can generate a surface, so we don't need to have the prior knowledge of the surface design, and we can do pretty funky freeforms with it as well. So they're contact metrology side, so we use a stylus, and the stylus contacts the component, as you're hopefully aware. Then we go to the non-contact metrology side, and on this we start with the Lufascan 50SL, which is a new addition to our Lufascan range, and that's really geared towards measuring high volume small lenses like mobile phones. And there's some really good tricks with this instrument. We can measure features like interlocks, like the internal angles, as you can see on the lens example I have there. We can actually even measure decenter and wedge between the two surfaces, so we can actually look through the lens surface with the non-contact probe, with the laser on the non-contact probe, and we can measure both faces in situ and give you decenter and wedge between them. So a very exciting instrument, and certainly has a lot to give in the industry. Then we go to the mainstay, I would say, the backbone of the Lufascan range. Both of these instruments have been around for some time. We do the 260 and the 420, which relates to the absolute measuring aperture that it can cover, and on these we can cover things from 90 hemispheres that go all the way to 90 degrees. We can do freeforms, we can do annular parts, we can do segmented parts, Really, as long as we can put in a definition for this surface, then we can measure it. Okay, and that includes complex A-spheres like gull wings, etc. And then something again which is quite exciting is another new addition to the family. So we've done small at one end, now we're going for the big end, and we can do 600mm diameter optics on the Lufascan 600, which is quite a large measurement capability. But going one step beyond that, for the end of this year, we'll actually have the first 850mm diameter measurements, diameter capable instrument available as well. So that's quite a big step forward. So this year we've gone small and we've gone large. Okay, so that's hopefully a good overview of our optics range that we have with the contact metrology, with the PGI Freeform Talysurf, or the PGI Optics, and then we go up to the non-contact metrology with the Lufascan. So on to astigmatism, the core of what this webinar is about. So, I mean, as most of you guys in optics know, astigmatism can have a dramatic effect on the image quality of the optics. If you haven't got the same radius in both axes, you can get distortion, or focus in one and get distortion in the other. Now, a full 3D surface measurement on a lens, using a Lufascan, for example, can quickly and easily allow astigmatism present to be seen. So how do we measure with a Lufascan? Just very briefly, for those of you that haven't seen this, we basically measure, we take a spiral scan over the surface of the optic, and in doing that, it allows us to very quickly and accurately collect data across that whole surface, which obviously allows us to see astigmatism. You can see an example of a measurement or a result down at the bottom here from a Lufascan. Now, I'll mention it now, but we do have a webinar coming up on the 22nd of September, and that covers an introduction to the Lufascan range and what they can do. And we'll be building on that with further seminars on applications in the future. So, although the PGI Optics measures in 2D, it is also capable of checking for astigmatism. Some of you may already have ideas on how we can do that, but hopefully this will show you a quick and easy way to do it with guidance as well. So in this webinar, I'll show you how we can do that. I'll also at the end show how it's possible to do Zernike analysis on the measurement result. So if you want to check for astigmatism, you wouldn't want to use two profiles, okay? If you have two profiles spaced at 0 and 90, as you can see from the example here, if you extract those two profiles along those two axes, they're actually very similar. So if you only took two 2D profiles, one at 0 and one at 90 degrees, and looked at them, you may look at that part and consider it to be a very good part with no astigmatism. But we know from looking at the 3D plot that it isn't. So if you actually want to see the astigmatism, you take your three profiles, okay? Now the three profiles, if you look at these 2D profiles here, you can see the two look similar, but there is a third one that's distinctly different, which suggests that there is a significant amount of astigmatism on the component. Now the PGI Optics software allows you to easily define a measurement sequence that includes radial measurements with a 60-degree spacing, as this example, but you could do it with a lower distance spacing. So you could do every 45 degrees, you could do every 10 degrees. It depends what you want to get from the measurement and how much time you have available. So these measurements, once we've taken the three measurements, what we do is we'll analyse them individually and then we'll recombine them to generate the results showing the form variation across the part. In the next couple of videos I've put together, the first one is going to show you how you actually set up a measurement for a component, and then the second one will show you how, once you've set that measurement up, how you would take it manually on a 2D system without any automated stages. Okay, so this is the part setup interface. So if you want to set a part up, you'd simply go, and first of all you'd enter the design for the part. In this case we're just using a simple radius, calling it an 80mm radius. You can check the design with the SAG, you check whether there's any issues when we measure it. Okay, then you move on to the measurement section, and this is where you choose how many angles you want to measure. Okay, now we're going to tell it we want to measure 3. Okay, so that's every 60 degrees. We can actually, although this is a manual system, we have the ability to help guide an operator through cresting in Y as well, which you will see when we go through it. So you can tell it here how you want to crest on the component, i.e. find the highest point or the turning point or the lowest point if it's concave. You can choose the analysis and you set that. You can choose how we want to apply a filter, easily set. All of these things can be changed at a later date again, should you wish to. Okay, and then you choose where to store it, and this is different for those of you that have seen Ultra in the past. This is where, when we store the measurement data here, we actually store it in a Windows folder structure. So we'll automatically put the results and the analysed surface into a folder that's easily accessible externally to the optics software through a standard Windows structure. So that's very briefly taking you through how you set up a measurement, but you can see how quick and easy that is. Okay, you define the design, you tell it the shape you want to measure, you decide how you want to measure it, how many angles you want to take, for example, speeds, how you want to crest. You tell it how you want to analyse it, optimise radius, absolute radius, filtering, do you want to look at slope errors, etc. And then you tell it how you want to store the data. Okay, so if we come through now, if we look at how you want to measure a part, so once you've defined a part and you've saved that, okay, now you can recall that at any time, and this is how you would select the part to measure it. So you come up here and you choose the part that you've just saved. Okay, you hit measure. Now at this point we start with dialogue to help you understand the stages that we're going to go through. So if you look here, what we're doing first is we're going to crest on the component. Okay, in this case we're cresting in X. Now that's automatic because we have always had the automated cresting in the X-axis. However, when we come to the Y-axis, we have no automation. So at this point we pop up with the Y cresting and we give the operator assistance with a value matching to look at a turning point up here that enables them to find the highest point or the turning point. And once they've done that, they can then click OK or yes, and they can move on to the next stage. Now the next stage, we've crested in X, we've crested in Y. The next thing we're going to do is actually take the measurement for the first orientation, and that's 0 degrees, remembering that we have chosen to measure in 3 different orientations. So that's the first measurement complete. So now what it's doing is it's going to actually instruct the operator that they need to rotate the component to the next position. Okay, now again, as I said, this is done manually. So the components rotated, and now we'll start the measurement sequence off for the second angle. Now because we've manually rotated this component, we need to go through the same routine again. We need to crest again in X and Y. So again, I've speeded this up, just, you know, it gets a bit boring otherwise if you want to watch it over and over again. But now you can see we've taken the measurement of crested in X and Y for the second angle. Now we're doing the measurement for the second angle, and then we quite simply repeat that procedure for the third angle. Okay, so now at the end of it, what you'll see is we actually have generated here is an average profile combining all 3 profiles, but we can go back to the first angle, we can look at the first angle. Okay, we can pick out the individual values for that analysis, we can look at the raw profile. We go to the result 2, that's the second angle, or we can go to result 3 and we can look at all of that. We come back to the average. Now the average is the profile you might want to export if you wanted to do a correction, for example. But most importantly, we come now and we look at the 3 profiles overlaid, and these ones start to show you whether you've got astigmatism in the component. So once you've done that, now say you've done that but you want to reanalyze it, you can quite easily come back to the design parameters and you can come in and you can correct the parameters and reanalyze. Say in this case, maybe you want to change the filter. Okay, so you could modify that if you wanted to. But what we're actually going to do here is we're going to reanalyze the part where we use 3D astigmatism. Okay, so what do I mean by that? That actually combines the residual 3 profiles that we took, where you saw the 3 overlaid, and it will generate a 3-dimensional residual surface. So this isn't full 3D in the sense that the loofah scan is, where it scanned the full surface and done the analysis. This is essentially a residual surface that's reconstructed or interpolated using the individual 2D profiles. But as you can see, it's really good. It gives you a very good visual representation of the rotational form errors that you have around the component or the part that you've measured. Now, once you've got that surface, we automatically save that surface as a text file, so you can use that 3D residual surface should you want to for something else you want to do corrections, etc. Or in this case, as I'll show you next, it's really, or in the next few slides, it's really moving on to how you could do a more advanced analysis on it. For example, Zernike. So I showed you there an example of how easy it is to take a measurement manually with the PGI Optics, and I showed you, hopefully you've understood how we can help operators in stepping through each of those procedures, automating the measurement and generating the results, combining the three profiles. Now, mentioning back at the start with the PGI Freeform, the PGI Matrix, and both of these benefit from the addition of motorized Y and rotary stages. So that allows us to move obviously Y perpendicular to the measurement axis in X, and it allows us to automatically rotate the component. In doing that, that gives us the capability to very easily measure a component or to automate the routine that you just saw. So as you see here, we've just crested in X and Y. Now we take a measurement, then we're going to rotate and we're going to crest in X and Y again. And we're going to take the second angle measurement. And then we're going to, once we've done that, we will then go on to take the third angle measurement. Now, I just hasten to add, this isn't the real speed. Obviously, this video has been speeded up for the demonstration, but it's to give you the indication, the example of how we can do it fully automatically, if that's what's requested. Okay, so we can easily measure a part manually. We can equally measure a part fully automatically if that's what's needed. Benefits of full automation would typically be that we remove any variances you might get from operator variance, or the difference in operator capability. Now, that was showing automation on the PGI Matrix and the PGI Freeform, but if you've got a PGI Optics, you can add different levels of automation to that. So just going through these, we could start with option 1, which is where you'd simply add a Y-axis. Now, if you add the Y-axis, how does that benefit you when you want to rotate the part? Well, what it would allow you to do is to automate the X and Y cresting routine, okay, which is really good because obviously it takes out any variances in manual cresting in Y. If you wanted to measure this part in the sequence that we've shown, you would hit go and it would automatically crest in X and Y, but you would have to manually rotate the component, okay, between steps, but you would be guided through that process with the measurement routine. If you go to option 2, option 2 is only having a rotary stage. Now, depending on your production methods, your production routines, this may be a good option. And in option 2, what you would do is you would center the part relative to the spindle axis or the rotary stage axis. Once you've done that, you would simply measure 0, it would automatically rotate, measure at 60 degrees, automatically rotate and measure at 120. Or, as I've said before, you could do it at any number of radial positions. But this would fully automate the measurement once you have centered the part. Then we go into option 3, that combines the X and Y, the Y stage and the rotary stage, basically giving you a smaller version, if you like, of the PGI Freeform or the PGI Matrix. So that fully automates and it would measure in X and Y, crest in X and Y, and then automatically rotate as necessary between the measurements. The benefit of this is obviously full automation takes that operator variance. On the other side, though, these stages aren't quite as quick at measuring as the PGI Freeform or PGI Matrix. However, the benefit is in consistency of measurements, and obviously it's operator free running. So you can put a component on, hit go, go away, start cutting a second part, come back, this part's finished measuring. Okay, so just a few ideas there of how you can add this automation to your PGI Optics, should it be something that that you wish to do. So you've taken the 3 measurements, whether you've done it on a PGI Optics, a Matrix or a Freeform, you've generated your 3D surface, as you can see here, but you want to do a Zernike analysis to really understand if you have or put a figure against or a strength against the astigmatism or indeed coma, etc. So within another utility in the PGI Optics range, we have the ability to define the terms that you want to analyze the surface with as a Zernike surface. So throughout this, you can see here, you can basically select the terms you want to. Now in this example, I've just selected all of them to show you what we can do. So you select all of those quite simply, you apply the analysis. This is the Zernike residual surface. Here you can see obviously it's taken out some of the form that is on the raw residual surface, if you like. And over here you'll get in the identity card, you get tabulated values showing you the strength of all of the Zernike components that are there. Okay, so that's hopefully given you an idea of how easy and straightforward it is, or quick and easy and straightforward it is to take to check for astigmatism on a 2D instrument, like say for example the PGI Optics or the PGI Matrix or Freeform. We've shown you how you get although not fully automated with the PGI Optics, we have the software capability to help hold operators' hands and step them through to give more consistent measurement results. Obviously, going to the PGI Freeform, you get that full automation. Okay, so hopefully there's been something of interest there throughout this webinar. As I mentioned earlier on the 22nd of September, we're doing our next webinar, which is an introduction to the loofah scan. Hopefully some of you will join us there. We're going to be covering the initial range on that one, and then we'll be following up with some other webinars going into more detail at a later date. Now, questions, and I have to apologise, I forgot to request that if you have any questions, if you keep those, and we go through those at the end. So for those of you that have been popping the questions in, it's really good to see. Sorry that I haven't been acknowledging them through the webinar, but I will go through them now. Okay, so one of the first questions, is there a good rule of thumb for the number of traces versus which Zernike polynomial orders can be analysed? That's a very good question. I mean, I would think it's, you know, if you're looking for astigmatism, if you're looking for a low order form error or maybe coma, then in my experience, then three profiles would show you what's there. 4 profiles will give you obviously a more accurate representation. But if you're going to some of the higher orders where you're looking at trilobing, things like that, then I would think you probably want to be going to maybe 6 or 8 profiles to start looking at that, because remember, we do interpolate between the surfaces. Certainly 6 profiles in my experience starts to catch some of the slightly higher order features. So 3 is adequate for your basics, but typically 6 you should start to see a lot of the higher order Zernike forms in there. But as I've said, you're not limited. You know, if you've got some really high order Zernike forms in there you want to have a look at, you could do 8, 12. Really, it's how many or how much time you want to put into that. So hopefully that's helped there. If you want to analyse Zernike, you don't do it directly in the PGI Optics, you would do it in Talymap. We have an additional utility on there that allows you to do the Zernike analysis, so it's quite simple and straightforward. At the moment, we can take the text file from the PGI Optics and you can input it into Talymap, or we actually have basically got the same functionality in Talymap that can be opened automatically from the PGI Optics to do the analysis in there if you want to include Zernike on that. And that's quite simply done by setting up what we call a template and choosing to run that template as the results engine for the measurement in the PGI Optics. And that's quite a seamless process. So once it's set up, you wouldn't have to reopen Talymap and reanalyzing that. It can all be done for you. Okay, so hopefully that answers that question. If anybody has any specific things you'd like to see an example of that, then feel free to contact us with the applications team that I have. We can always give you a demonstration. Slope errors in 3D. Good question. At the moment, we can't do slope errors directly in Talymap, which is where we'd be dealing with the 3D surface. What I would say is, to be honest, with the level of resolution that you get from the PGI Optics, I would question the value of the slope errors that you get. We can do slope errors on the 2D profiles, and you could do those, we do that automatically on the 0 in this 3D profile. We do it automatically on the 0, 60 and 120 measurements. So you could do it on there, but I would probably think if you really want to look at higher slope errors on a 3D surface, you really want to be looking at something more along the lines of the Lufa scan, where you get a higher resolution of data over the whole surface. Okay, so thank you very much for joining me. If you have any more questions, then please feel free to contact us at Taylor Hobson, and I will do my best to answer. Okay, so as I said, thank you very much, and hopefully you've got something from this, and speak to you soon. Thank you.